Merci beaucoup. Thanks for inviting me and for bringing us all together here. I want to give a talk about Motivic nearby cycles. Maybe with the idea of how they are useful in geometric representation theory and hopefully also in the Langlands program, but this will be more sort of in the background of my mind. Since I have a little bit more time than usual, I will begin with a recap on Motivic sheaves, just to give you a very sort of brief introduction to this. And then I will talk about the joint work of Robert Cass, Thibaud, van den Hove, and myself on central motives. And then I will end this lecture with some more speculative ideas that are joint work in progress with Timo Richarz. Okay. So that's my plan, and let's begin with this short recap on Motivic sheaves. So, what's the definition? So X is some scheme, not too crazy scheme, let's say a finite type over a field or over the integer or something like this. And then there is the category of étale motives on X, or étale motivic sheaves, whose definition is surprisingly compact. So I will write it down as follows in steps. So it's, first of all, the idea of this category is you want that geometric objects over X are somehow in this category. And so technically one takes the category of pre-sheaves on smooth schemes over X with, in this talk I want to focus on values in the derived category of abelian groups. Of course, this doesn't do all that much. And so in there, you look at sheaves that are homotopy invariant, so which I denote by this A1 here, so sheaves which are not distinguishing between some y and y times A1, and that they are also supposed to be étale sheaves, or in the fine print they might want to be étale hypersheaves, which I don't want to discuss too much. Yeah? So think of this as being some sort of homotopy invariant sheaves on this pretty big site here. So this is the so-called effective category of motives. And then in there, there's a certain object, the so-called Tate circle. So T is going to be the cofiber of the inclusion of Gm times X sitting inside A1 times X. Yeah? So these are clearly representable pre-sheaves here, so we can view them as objects in here. This cofiber makes sense, and this is usually denoted by Z twist 1, and this Z twist 1 is tensor inverted in a formal way. Okay, so there's a certain formal way of rendering this object into something that has a tensor inverse, which will be denoted by by Z twist minus 1. Okay, so that's the definition. And so you might, okay, I mean, if you have never seen it, maybe it sounds crazy, but it's surprisingly powerful. And I want to make a little comparison between this category of motives and the categories of classical étale sheaves that are commonly used. So here is my little table. So what happens for this category dm? I want to talk about a few aspects, of course, only not nearly everything. And then by comparison, what happens for the category of étale sheaves on X, let's say with coefficients in some ring lambda, where lambda is Z mod L, where L is prime to the characteristics, or maybe you want to have ZL or QL, depending on the situations. Okay, so these are, I want to compare them. So the first criterion that I want to mention is, let's say, are Hom groups computable? So in other words, can we honestly compute these, what this category spits out? It turns out answer is no. I mean, in the following sense, I mean, they are computable, but not practically speaking computable. So the following fact I want to mention, so this Hom in this category of motivic sheaves, from the constant sheaf to Q twisted and shifted like that, this would be the nth Char group of X with rational coefficients. Okay, so in other words, I mean, we can compute this theoretically speaking, but of course, if anyone asks you what's the rank of this group, then this will be tough. Oh, sorry, I should have said, of course, I mean, I think it's clear, but So of course, none of this is here due to myself, but rather we should thank Joseph Ayoub for his work and also Szynski and de Vries. So pretty much everything I say here is appearing in their papers. So okay, home groups are not quite computable, but at least related to algebraic cycles. Whereas in here, of course, we have a good feeling about what these Étale cohomology groups look like. So that's a bit more accessible. And why do I put these two things here side by side? So there is the so-called rigidity theorem that I want to mention. Rigidity theorem, again due to Ayoub, which says the following. Which gives basically a link between these two sides here. So the link is, so maybe I will put this here. So if I take this category of motifs and I just artificially change the coefficients by replacing z by z mod L, which I can do by performing tensor product over d of z with d of z mod L, then I get exactly the category of Étale sheaves with z mod L coefficients, where again L is prime to the characteristic and under some mild assumptions on the x. But basically, this line here is telling you that this category of Motivic sheaves, it interpolates on the one hand, you have for all these L's, you have all these categories of mod L sheaves, which we know and love, and then there is some rational component which is, I mean, among other things, seeing the Chow groups, and this is kind of what this category interpolates between. And so, yeah, that is some useful black box to know. And another good piece of information is that we have 6 functors, of course, for classical Étale sheaves, and they also exist for motifs. So this is very much the same story. So there is, technically speaking, a functor from here to there, which commutes with all 6 functors under some small finiteness assumptions, but sort of you have what you want to have there. So that's, of course, a foundational tool in the usage of analytic sheaves, and so motivically this works as well. So what's another asset that we keep using when we work with Étale sheaves? We keep using the perverse T structure here, which we don't have motivically, or at least it's not known. So let's say no, and I will comment on this later. So this is not known in general. So we don't know how to split a motive into its pieces whose realizations under this functor going from right to left would be the individual cohomologies of that variety. We don't know that. So that's one of the bottlenecks motivically. And another criterion that I want to mention is, so I'm alluding to it a little bit imprecisely. So let me call it cases of contractibility. So maybe this is not standard, this term. So what do I mean by this? So I'm wondering the following question. So let's say we look at a map F, and we basically just want to have that this functor F upper star is fully faithful. Yeah, this is technically what I mean by this. So when does this happen in the context of Étale sheaves? This happens, I mean, a number of times. For example, when you have spec R, a strictly Henselian local ring, local ring mapping to spec of some, let's say, separably closed field. Yeah, then these are both. These are both. I mean, then this pullback from sheaves here to up there is fully faithful because the cohomology of this thing behaves like it if it was a point. And so let me also note that if this spec R here is replaced by another separably closed field over this smaller separably closed field, yeah, then this is even an equivalence. So let's say F, then F upper star is an equivalence. Okay, so that is something here. And what by contrast, on the side of motifs, this is this happens practically never. The only case when this actually happens, or well, maybe not the only, but let's say at least initially the only thing when you are seeing this is the projection from an affine line down to S, because we have basically rendered the affine line to be isomorphic to S. Yeah, so it's somehow by fiat that the functor P upper star here is fully faithful in this Motivic setting by the definition. Okay, so this is, I mean, maybe you wonder why do I mention all these things here? So I hope it gives you some sort of an idea what we sort of can take advantage of, and other problematics, other features which are, well, not true or not known. Yeah, and so I'm bringing these here up because they are going to play a role later on. I want to introduce a brief notation, which is going to come up a lot in this talk, and also, I believe, in Thibaud's talk. So this category of so-called Tate motives, DTMX, so derived category of Tate motives, this is defined to be the category of the full subcategory of DM, of this category of Motivic sheaves, generated by all these Tate twists under all colimits. Yeah. So roughly speaking, one can think of those as being kind of the constant sheaves, but the crux of the story lies in what the extensions are between these sort of constant sheaves. Yeah? So it's not that simple in the end, but maybe as an approximation. So, and as an honest statement that's not an approximation, let me say this. So DTM of, for example, a finite field, if I do these rational coefficients, yeah, if I don't do z coefficients but q coefficients throughout, then as you can maybe guess, so here I said certain home groups are Chow groups. If I had put another combination of twists and shift, this would have been another piece of algebraic K-theory. So in other words, this category sees not only the K0 but also the higher K-theory. But for such finite fields, this collapses. It's only sitting in degree 0. And this is why this is the same as the derived category of graded Q vector spaces. So this DTM of a finite field is that simple. And for other fields, this would see whatever the K-theory of this field is. And somehow, in some sense, the philosophy, or I don't know, the spirit of much what I'm going to say is you're supposed to think of this DTM of your ground field as some sort of a black box that we would like rather not to touch because this amounts to computing K-theory, which is really hard, but kind of working relatively over this ground field, we want to try and understand what happens. Yeah, this is kind of the spirit. Over Z, yeah, it's tricky. I mean, you see, I mean, if you are over Z, then you will have certain extensions because Motivic cohomology of Z is non-trivial outside degree 0 still, and so then, I mean, it's abstractly isomorphic to modules over a certain graded E infinity algebra, and the cohomologies of that would be the K-theory of Z, up to this mixture between L-adic, I mean, mod L and so, but more or less that's the picture. Yeah? So it is what it is, and it's hard to say much more about this. Okay, so now I want to, after this brief sort of introduction, I want to move to the work with Robert and Thibaud. And I'm trying to kind of gear this talk towards seeing everything from the angle of these nearby cycles. So let me begin with this. What is the situation here? So S is some base scheme, so think of S as being some spec K or maybe spec Z, whatever, something like this. And then these unipotent nearby cycles, motivically, work as follows. So the geometric situation is we have some geometric object, maybe some scheme or even an in scheme or a pre-stack over A1. Okay, so this is given. And then I want to introduce some notation. So we have GM here. And X eta, this is, I call this the fiber of over GM, and this I call F eta. And then we have the fiber at 0, which I call XS. And this I call I and J. Okay, so that's the geometric situation. And now what is the unipotent nearby cycles functor? It's the following functor. So I denote by upsilon, and I write upsilon mon for monodromic. So this is some subscript that I will comment on in a moment. Let me first define it. So it starts where it takes as an input a Motivic sheaf over X eta, And as an output, it's supposed to produce something on the special fiber. Of course, the most naive thing is to just to do J lower star and then I upper star, but that would not be, I mean, so smart because, yeah, it's just too simple. What the functor is the following. So it's, here is some funny functor, gamma question mark I call it, and I will say what this is. And this lands in dm x eta tensor over dtm s dtm gm. So I think maybe now I write the s one more time, but then I will drop it. That's the first sort of stop of this functor, and then I do the I upper star J lower star in this component here and just the identity here. And so I land in dm xs and then tensor, and from now on I will drop this subscript dtm of s. Yeah, I will not write this anymore, just to save some time. But of course I do keep the dtm gm. That's the functor. And so I have to tell you what the gamma question mark is. Maybe I'll do this in one moment. Let me first define upsilon f without the mon. So upsilon f is just, you take this upsilon mon, it's a monodromic functor, and append to it the pullback along the point 1 in the gm here. Yeah? So notice I have omitted the dtms here. If I pull back from gm to 1, then these two factors will cancel. So this is going to be a functor from dm x eta to dm xs. Okay, so this is a definition here. So it's called unipotent nearby cycles functor. And now I have to say what this gamma question mark is. Gamma question mark, what is the idea of this functor? Once again, it takes as an input a sheaf on this sort of quote-unquote generic fiber, and is supposed to spit out something in here. What is the idea behind it? So this, whatever sheaf lives on here, I mean, pretend for a moment, you forget everything about motives, pretend this was some scheme living over an affine scheme. And then you would know that any quasi-coherent sheaf on an affine scheme is not only a sheaf of abelian groups, but actually a sheaf of modules over that ring that we see down here. Yeah? And something similar happens here. So this functor just records the action of sort of the Motivic homology of GM on this. So let me write this down formally what this is. I mean, formally it's very easy to say what it is. So this gamma f eta question mark is the right adjoint of the natural functor going this way. So it goes once again from dm x eta tensor dtm gm to dm x eta. And what is that functor? Well, it takes a sheaf on this x eta, another sheaf on gm, and simply takes this f tensor f eta upper star of g. So in other words, this is simply the natural way how this category dtm of gm acts on here by pullback. Yeah? So similarly to the way that modules over the ring, let's say R, would act on quasi-coherent sheaves on this thing over spec R. So this is an obviously existing functor, and it has a right adjoint, which we can contemplate and use here. Okay, so I want to shed some more light on this term here in the middle. And in order to do this, let's observe that dtm gms admits a very simple description in terms of this dtm of s. Namely as follows. It's going to be modules over, so p lower star of z. So p is the structural map from gm s down to s. So this p lower star of z will be an object in Tate motives over a point, namely this. Let me say what this is. Maybe, yeah. Let me first write this here, dtm s. So let's say what this is here. So this is an object that, at least without looking at the multiplicative structure, is z plus z twist minus 1 shift minus 1 inside this DTMS. Okay? So once again, think of this DTMS is basically, think of this as being more or less graded complexes of vector spaces, if you like. And this is a certain two-term object here, which we can look at, and we can look at its modules. And so this admits a description using some causal duality argument, which holds true after rationalizing. So after rationalizing, this thing here is a square zero extension, and then there is a fact which tells that this is admits another description, namely as something that I denote by nilp DTMS. So nilp stands for nilpotent, or locally nilpotent, strictly speaking. So what is this? This is the full subcategory of modules still in this DTM of X, yeah, of S. So remember, I want to treat it as a black box, but if you don't like this black box, think of that case. Over what? Over the symmetric algebra of basically the dual of this guy. Yeah, so this causal thing gets rid of this shift, and then it will replace this by its dual, and that's what I'm looking at here. So the full subcategory of this, So the incompletion of the full subcategory of this generated by just Q, regarded as a modulo over this via the augmentation. Yeah, so if not for this twist here, we could think of this as being a polynomial ring, and then this would be would be similar to sheaves on the affine line that are set theoretically supported at the origin. This is kind of what this does here. But whatever it is at the very least a certain full subcategory of this. And so in other words, an object in here we can regard as some M together with an action of this thing here. And so let's say M plus a map from M twist 1 to M. Yeah, these are the objects that this DTM GM cooks up. And this functor 1 upper star that I wrote here would just amount to forgetting this extra map. So in other words, then we will forget this extra thing. Huh? What? Oh yeah. Thank you very much. No. Well, this is modules over this inside here. So that's the parenthesis, if you like. Yeah, thank you. Other questions so far? So this is what this second factor here is, and then there is some higher algebra nonsense which tells that this thing here is just maybe let me just, for brevity's sake, just write it's a full subcategory of modules again over the symmetric algebra Q twist 1. So after rationalizing, only this is true inside now here. Yeah? And so, in other words, this first functor just tells you how this operator somehow comes about. But you see, it's somehow abstractly very simple. Okay, and so of course the same description, maybe more importantly, is true over here, where here we now see a sheaf on the special fiber together with this operator. Yeah, so this upsilon mon takes a sheaf on the generic fiber, spits out a sheaf on the special fiber. Well, of course, it's not going to be one by one object, but sort of, morally speaking, a sheaf on the special fiber together with this operator. Okay, so that's the definition. And of course, this doesn't come out of the blue, but rather there was a construction which is much, much more complicated due to Ayub. So here is a theorem due to in the paper with Robert that I mentioned, and Thibaud, Van den Hove, and myself. This definition agrees. This definition of upsilon agrees with an earlier definition, let me just say it orally, much more complicated definition of unipotent cycles, nearby cycles by Ayub. And it is also So you see, this doesn't use anything about motives. This is really just a general play with 6 functors. So you can also apply it to sheaves, for example, in the Betti context, and there it reproduces Beilinsen's approach to unipotent nearby cycles for Betti sheaves. Okay, so this is the right thing to do in the context where we only care about a little bit of the nearby cycles, in the sense that, well, you can already guess that we will have to talk about what happens with this if we don't want to do this DTM here. So I want to include one sample computation just to convince you this. I mean, it looks crazy, maybe, this right adjoint, but it's somehow still computable. And so I want to do a toy example. Huh? Yes, I mean, this is only using z coefficients. Yeah, it doesn't need anything else. I mean, it's even. Yeah, I mean, what does use rational coefficients is this description here of this category. Because integrally, it's not a square zero extension. But okay, maybe that's a detail. Let me give a toy example. So let's look at the case when x is a1 itself over a1 by means of the identity map. Okay, so let's compute the unipotent nearby cycles using this formula in this stupid case. So I claim that this takes the constant sheaf and produces the constant sheaf. Of course, this was, I mean, obviously known to Ayub because, well, he knew this. I mean, but here's a slick way of seeing it. So let's write down some diagrams. So we start, in this case, not on dm. So notice in this case now the generic fiber is gm itself. And I want to look at not at all sheaves, but rather only at Tate objects here. Yeah, so such as the constant sheaf. And then this gamma question mark is really, so this gamma, this graph of this map here is going to be the diagonal. So I write delta question mark, and it will land in DTM GM tensor DTM GM. And then I now want to split up these two steps into two. I first want to do the J lower star and then stop there. So let's do this. So J lower star, this will land in DTM of A1, where here I'm using a little bit of an abuse of notation. So here DTM meant only things generated by the constant sheaf. So here I really mean sort of stratified by A1 as A1 is GM union 0. So I want that the restriction to GM and to 0 are Tate motives in the sense before. If I do this, then I have more. I mean, then J lower star of Z will be in there. So this is where I land, and then I have DTM GM. Okay, and the next step that I would have to do is that I need to do is the I upper star. What about this? So let's write this like this. So I upper star, this will land in, so I will replace this A1 by 0, and once again, remember this tensor product is over DTM on a point, so this will cancel with this thing here. So I will be in DTM GM in that situation. Okay, this is sort of the definition. And now how can you compute it? So you can compute it by using another functor here. So let me write Q lower star. So Q is the structural map from A1, S down to S. Again, I can push forward a Tate motive on A1 down to a point, which again will make this factor go away. And again, I land in DTM GM, okay? And then there's, of course, these two things are the same category. And what's also true is that these two functors are the same. So let me maybe write such a thing here. So what I'm saying is for such a Tate motive on A1, doing push forward or restricting to 0 amounts to the same thing. Yeah? And which is true because of this homotopy invariance there. Yeah? So we are using this case of contractibility there. So by A1 invariance. And what does this buy us? This buys us the following. We can, instead of considering this composite, we can rather look at this one here. We still have to somehow come to grips with this abstract right adjoint, but we see, luckily, this is a right adjoint, this is also a right adjoint. So let's rather look backwards. What is this functor? So it's going to be, I mean, by the orange one, I mean the left adjoints. Yeah? So here this would be J upper star, Q upper star, and here this was this mysterious right adjoint of a natural functor, which is basically delta upper star. Yeah? And so you see, we start on GM, we pull back to an extra A1, right? This was this Q here. Then we restrict to GM times GM, and we go using the diagonal to GM. And so you see this composite is clearly the identity, and so therefore this orange left adjoint here is also the identity, and therefore this right adjoint, including this mysterious delta question mark, is also the identity. Yeah, so this, maybe let me just say tuck, 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 this is the identity. Yeah, and therefore also tuck, tuck, tuck. Okay? So this is, I think, a nice little sort of way of seeing how the foundational input of homotopy invariance is basically more or less equivalent to this computation here. Okay, good. Now, this is all I want to say about this general definition and its most basic properties. Now comes the tricky part of the talk. Okay, luckily I have one more board, so I can postpone the problem. So now I want to talk about this application to central motives, just to somehow embed this into the context of the meeting here. So I guess maybe it's boring to 95% of the people, but okay, let me still say it. Let's say G is split reductive. And then, of course, we have the isomorphism by Bernstein, looking at functions on G on the loop group, basically. Tuck, 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 modulo the positive loop group over FQ, and modding out one more time. And so Bernstein tells us this is the center of the Iwahori algebra, consisting of functions on the double quotient of the loop group, modulo the Iwahori on both sides. Okay, so that is the starting point, and then of course, as you also all know, comes Gaitsgory's work, which sort of successfully takes the geometrization of this. And I want to mention, just because this was very useful for us, also this book by Ashar and Risch explains this in all its glory. So the geometrization of this is the following. So there is a functor. There is a functor, maybe also called Z, from L plus G equivariant sheaves on the affine Grassmannian to perverse sheaves on the I equivariant sheaves on the affine flag variety LG mod I. And of course, it's not just a functor, but it has a bunch of beautiful properties that I don't want to somehow rehash here. But I want to say how it connects to the previous part, which is maybe the most important piece of information for the moment. There is a functor like this, and this is given by unipotent nearby cycles functor along a certain family. So it's some certain moduli space which lives over A1, and its fiber at 0 is the affine flag variety, and its fiber over GM is basically a product, so more precisely GM times the affine Grassmannian for the group times the affine flag variety. And Gaitsgory's idea was to use this family and to use nearby cycles to come up with that functor. And so I don't have anything to add to this. What I do want to add is this works also motivically. So theorem, again, due to Robert, Thibaud, and myself, mostly, is the following. So what I'm going to say is basically all of this carries over to the context of motivic sheaves, which, among other things, buys us, as you can see from the definition, that these motivic sheaves are independent of any choice of L, and they work over any base scheme, and they have all these Tate twists. So it's really, in my opinion, the finest and most universal comotive theory that we can use here. It's also, maybe let me just say it orally. I mean, I focused on this case of étale motives here. There is a version of this for Nisnevich motives, which has the property that it works over any field. And if you are over Fp, it will also allow Fp coefficients. So this is a nice comotive theory, maybe for modular representation theory as well. But anyhow, what is the statement? So let me, it's a bunch of statements. So first statement is, this is actually due to an earlier work with Timo Richarz and myself. If I look at DTM of the affine flag variety, for example, or the affine Grassmannian as well, so this is not specific to this one example. So by this I mean these are motives in the category, in the full category, which contains all crazy wild objects, and the condition is that M restricted to all these, in this case, Ibahori orbits here are actually a Tate motive on this Ibahori orbit. So the first statement is this is a well-behaved category. Is well-behaved. What I mean by this, let me just say it orally. What you have to check here is one thing, namely that basically we would like to apply this gluing paradigm of Faisseau-Pervers and so on. And so we have to check that if we are on one stratum, we go to the closure of it and we pull back to something inside that closure, that this preserves Tate motives. And this is the case, and that's what I mean by is well-behaved. Okay, that's statement number one. Statement number two is over. So this works over any, let's say, over any S here, and now over S, such as spec Z, a finite field or number field, or in general any base that satisfies the so-called Beilinson-Soulé vanishing conjecture. This category here carries a T structure similar to the perverse T structure that is employed in these kind of statements. Yeah, so this is, I'm saying this in order, or I have now the opportunity to come back here. So here we have the perverse T structure somehow for free because everything comes as a derived category of an abelian category at the end of the day. Whereas here, this is really not known. It depends on this Beilinson-Soulé vanishing conjecture, which we know in a few selected cases. And the work somehow going from this kind of base point in some sense to these objects lies in sort of realizing, okay, all these strata are reasonably cellular and so on. Yeah, this is kind of what goes in here. Okay, so we are entitled to talk about T exactness, and let me denote MTM of L, the heart of this T structure, so mixed Tate motives as opposed to DTM for the derived category in some sense. Okay, now I have to. No, sorry, I should have. Maybe like that. And, oh, no. So at least you can see this for a little bit still, and then the other one I have to erase. So we can work in this very, very small subcategory of all motivic sheaves consisting of these stratified Artin Tate motives, yeah, which are the ones that are kind of, in some sense, pointwise Tate. Well, pointwise is more strata-wise, let's say. And that entitles us to talk about this about this T structure and entitles us to ask whether some functors are T exact or not. And it turns out that in this case it is the case. Yeah. So, okay, these categories carry a T structure that is meant to be a motivic replacement for the perverse T structure. And also, statement number 3 is, this space X that I didn't really talk about is going to be stratified by what? Over the special fiber, we are going to take the Iwahori orbits. On the generic fiber, we take Gm times the L plus G orbits times the Iwahori orbits. That gives some stratification, and that is again well behaved. So let's say the stratification of X by, let's say, Gm times, let's say, L plus G orbits times I orbits. This orbit is the generic fiber plus 0 times I orbits is again well behaved. So the technical term we use is Whitney-Tate. This is a term going back to Zirkel and Wendt's work, is Whitney-Tate. So i.e. well behaved in this line here. And let me say again what this means. So i.e. if I do I upper star, J lower star, sorry, now I cannot jump that high, but think of the first map being the J and the other one the I. As usual, I upper star, J lower star sends, or let's say preserves stratified Tate motifs. Yeah, and again, this is not completely trivial. You really have to do some geometric argument why certain closures of strata are somehow under control. Yeah, this is not is an honest geometric statement that doesn't come for free. Okay, so it does preserve Tate motifs, and so in other words, we can use the nearby cycles, which I just erased. Let me write them here again. Just so upsilon was defined. First of all, it was basically I upper star, J lower star. That was the part relating to the geometry of the X, and then the other one was this gamma F eta question mark. Yeah? And so you see here, this gamma F eta question mark will not ask about being Tate or not, so this just records this action. And this I upper star, J lower star, that will ask about this property. And so what I'm telling you here is that this functor preserves Tate motifs. And it was not clear to us for some time that that's enough to ensure that nearby cycles also preserve Tate motifs. So anyway, the upshot is this upsilon or upsilon mon of this X there is a functor from dTm Gm times Gur times Fl to dTm of the special fiber dTm of Fl. Okay, so we have this functor, and what's more is this functor here is T exact, similarly to the fact how this was in Gaitsgory's work, for example. So it is T exact, which again is not completely for free because you have to do a certain geometric argument for this. Yeah? So all these statements, they come at the expense of really studying these geometric objects at a pretty close level in order to make sure you never use something like art in vanishing. For example, here in the context of état sheaves, we have art in vanishing, so it's an immediate impulse that if you have an affine map, then push forward will be right T exact. None of this is available in that generality, and so we have to come up with specific arguments here. Okay, and so it is T exact, and therefore we can restrict it to MTM, and then sort of all the properties that were known for from Gaitsgory's work carry over to this functor, to this central functor. So we have a functor from MTM to MTM, which is once again a motivic refinement of all of this functor Z that I mentioned earlier. Okay, so far so good. This is the application of this unipotent nearby cycles functor in this particular geometric situation here. Any questions so far? Or while I erase rather a board? No, damn it. I erase this board and will lower the other board, and you have time to come up with a question if you want. In the next part of my talk, I want to talk about some more speculative thoughts, which are meant to hopefully one day be useful in more arithmetic situations. Because you see, what made all this work was the strong, the strong presence of these cellular stratifications and all this GM action and all this. Yeah, so this is very, very combinatorial in some sense, and so Timo and I are still scratching our heads on what to do in hopefully some motivic approach to Vincent Laforgue's work. And so what I'm trying to talk about now is an unfinished collection of thoughts somehow in that direction. But I hope you will still enjoy it somehow, even though it's not finished. So let's say towards arithmetic applications, let's say. So this is in progress with Timo Richarz. What is the goal here, or some of the question that we are trying to, in some way or another, answer? Here is the question. So the question is, what is a motivic analog? It sounds very stupid, the question that I'm posing, but here is it. What is the motivic analog of the forgetful functor from locally constant sheaf on some nice scheme, which we can also think of representations of the étale fundamental group, let's say with QL coefficients maybe. And then of course we do have the forgetful functor here, which is a tensor functor and which is a conservative functor to QL vector spaces. So of course, it's obvious what this functor is, right? But it's by no means so clear what sort of is actually happening here. And that's what we are trying to somehow get an idea about. So let me give a few sort of attempts to answer this question, which however all have their limits and their drawbacks. So one attempt one is not to allow all general motivic local systems or all dualizable objects, but maybe only a few of them. So and this was pioneered by Delin and Goncharov, and was later picked up by Hainaut and Levine. So what did they do? They looked at P1. So X here was P1 minus a bunch of points, minus X1 up to Xn. So over some field K. So this K was a number field for them, and these points are rational points. So that's the geometric situation. And what they did, so let me give a name to this structural map. So I call this P down to spec K. And so what they in essence did is the following. So they looked at this category DTM of X. Yeah, so now no stratification is present. We really look at the category of motivic sheaves on X, just generated by all these Tate twists. That's what they look at. And like before, so is it still here? Yeah, it's still there. So up there I wrote DTM GMS is this modulus over this cohomology by a monadicity argument. And the same thing, I mean, this was not specific to GM, it was true in general. And this is also going to be modules over P lower star of Z. Well, they worked with rational coefficients. Let me put Q inside DTMS. Yeah? So critical here is that the motive of this curve is a Tate motive. So this makes sense to write down in the first place, and it's also true. So this is this here, and so let me write this down in a similar fashion as over there. So this P lower star Q is just Q plus, and then a sum from 1, let's say, up to, I mean, I write it in a bad way, to n minus 1. Let me write it this way, and then Q twist minus 1, shift minus 1. Yeah, like before. So we have n minus 1 copies of this Tate twist, and again inside DTM of this number field. So why did they choose a number field? They chose a number field because they wanted to make sure this category of DTM of K has a T structure. So inside here we have this MTM. Yeah? So notice earlier I talked about this case here of Q, but I could have said, or I think I did say, it can be a number field. So this is why this has an abelian subcategory of mixed Tate motives. And this one here has as well. And what they did is basically observe that you have a functor from here to there, which is you pick yourself some point in P1 and do pullback along that point. Yeah? And this gives a functor like this. And it is conservative, much like before. And in some sense, this fact here entitles you to say, okay, the Motivic Galois group, whatever that means, is free of, in this case, rank n minus 1. Yeah? So pi 1 Motivic, in this particular case, is free of rank, in this case, n minus 1. Okay, and they used this and later on Brown to do things with polylogarithms and so on. So this is a rich story. But however, for the purposes of the talk that I want to, or of the questions that I would like to give here, it is somehow falls a bit short in the sense that it only allows Tate motives. Yeah? And so if I want to be an arithmetic geometer, certainly I should allow not just Tate motives. So that's the downside. And what's another issue is that, is the following remark, that on the entire category of Motivic sheaves, it is not true, it's emphatically not true that if you choose a different point other than the x, that these pullbacks will be isomorphic. Yeah? So there is not really, I mean, we think of this as a fiber functor, but motivically there is no such fiber functor because these fibers are really genuinely not isomorphic. Yeah? So on that bigger category, we have that problem on top of it as well. So, okay, but still it's interesting to me because it kind of gives maybe the idea that we can, in some sense, want to describe one category relatively to another, and that is sort of supposed to be somehow the Galois group, whatever that means. And now, so that is an interesting attempt that, however, only works in a pretty restrictive setting. And I want to mention another sort of observation that hopefully makes it clear that this is not a totally stupid question that can be answered in I mean, you know, just by writing down something simple. Because I want to say, how do we do this in the context of étale sheaves? Yeah? How can we understand this functor in some sense in terms of six-functor speech? So comparison, let's say the case of étale sheaves. There, what we would do is the following. So let's focus on a special case first. What happens when X is spec of some field, K, right? Then we would like to forget the action of the Galois group. So how do we do this? Well, we do this by basically taking P is the map from spec K bar to spec K, and then this forgetful functor, maybe let me give a name to it, U, is just P upper star. Yeah, so just pull back along this map. Okay, so that's simple enough. However, this is not working motivically because this category of motives over spec K bar is by no means sort of simpler than this one. Yeah, so this is just not working. So this doesn't work motivically because dm of K bar is not easy in the sense. I mean, you know, this is not really doing a good job here, I think. What is another way of trying to come up with something like this? So let's again be in the case when x is spec K. You might object, okay, aha, well, earlier he said, okay, we should try to think of motives on this base field as being the black box, and we want to treat this as somehow simple. So let's try to implement this idea. So let's go again to spec K bar, and maybe then, so think of this as being some function field. Maybe we go to its algebraic closure, and then we can go to spec of our ground field. Maybe this is a finite field or whatever. Yeah? So this is our sort of easy, quote unquote, easy ground field, and we could do P upper star and then Q lower star. Okay, that at least has the merit of landing in a supposedly simple category. However, it's also not good because already this is not, you know, it's not a tensor functor, right? The monoidal unit here will pull back to the monoidal unit, but then you pick up the entire motive of this very big field here. So that is not monoidal. And also, I guess, not conservative, and so on. Yeah. Okay, so in other words, I'm trying to say whatever we do in the context of analytic sheaf doesn't directly sort of copy-paste. There is no copy-paste solution for this. And so what I'm suggesting, and I mean, this is certainly somehow known, is that maybe it's good to use nearby cycles for such purposes. So why do I, or how does this make sense? It makes sense as follows. So there is a lemma in a paper by Tsong Chu. However, she says it's well known, but I don't know if it was actually well known. But in any case, what she says is F, so some étale sheaf on some scheme X is a local system. Some constructible étale sheaf is a local system if and only if all these specialization maps from between all these stalks are isomorphism. So I can pick a stalk at some geometric closed point and a stalk at a slightly more generic point, and there will be these specialization maps, and these need to be isomorphisms for the thing to be a local system. Yeah? And since we want to sort of try and understand this, it seems to me that this is kind of a good cue. And what's true is the following theorem due to Benedict Preiss, who is a student of Szynski, that there is some content to this motivically as well. So here's the statement. So I have to put some assumptions. So X is spec R, an excellent, strictly Henselian discrete valuation ring. Okay, and so we are trying to say something like this here. So M is going to be a constructible Motivic sheaf on this spec R here. And then there is, so we can regard this X as lying over A1 by choosing some uniformizer, right? And if we do this, we have the quotient field and the residue field. Okay, so we are now in this geometric situation of before. Benedict Preiss shows that M, so this is the assumption, and then she shows that M is dualizable if and only, and this is meant to be a replacement for being a local system. It's dualizable if and only if a certain natural map between I upper star of M, there is always a map to the nearby cycles of J upper star M, if this map is an isomorphism. Yeah? So this is the translation of this. So we cannot, in the context of Motivic sheaves, it makes no sense to try and say the two fibers are isomorphic because they don't even lie in the same category and they are in non-equivalent categories. But this usage of nearby cycles sort of takes care of this defect. Yeah? So we take our sheaf here, we take our sheaf on X, we restrict it, do nearby cycles go over here, and this is supposed to be the special fiber. And if that happens, and only then, the thing is dualizable. Okay, that is encouraging. So I want to say what the psi is. So the psi is very close to the unipotent nearby cycles. Maybe I write it over here. I have to speed up a little bit. The psi is the full unipotent, not the unipotent, it's the full nearby cycles functor as opposed to the unipotent one. Again, due to Ayub. Let me quickly define it and say how it relates to this other exposition that I gave before. So here, for the rest of the talk, I want to focus on that we work always in characteristic 0. So this is not necessary, but simplifies the talk a little bit. So let's do that. And now what is psi? Is the full nearby cycles functor, which is defined as follows. So psi of m is basically a kind of a certain averaging of the unipotent nearby cycles functor. So here's the definition. So it's u epsilon of fn of en upper star m. And what is this notation? So we are on x. X is our spec r there in this case, but this definition is in general. This is over A1, okay? This is my f. And then on here I have the nth power map, which I call En. And so like this, and I can pull back and I get something else, which is xn, and this is fn. Yeah? So we pull back our sheaf on here along all these finite branched covers of A1. Then we do the nearby cycle functor in the unipotent way, and then we sort of let n become more and more divisible. But it's actually a fact due to Ayub that this will stop when m is constructible. Yeah? So this is the definition. And so, okay, this is cool. And how can we maybe relate it to to this kind of formula over there with the u epsilon that I wrote? Yeah. Here is a little amusing insight. So this psi admits a very simple and similar description to the u epsilon. You remember the u epsilon basically only took into account the dTm of Gm, which means only the cohomology of Gm itself. And here we are going to allow a little bit more. So this psi is the following, let's say is equal or isomorphic to the following functor. So we go from dmx eta again to dmx eta. And now instead of taking dTm, I will allow something more general, namely datm, I call it, for artintate motifs. Yeah, so here this is again some functor of the type gamma question mark, except that I allow myself a little bit more sort of, I don't want to forget as much in some sense. And then from here we do the usual I upper star, j lower star in order to land in dmxs tensor datm of gm. And maybe let me say, just to avoid any complications here, k is for now an algebraically closed field of characteristic 0, and s is this spec k, just to get to sort of not wonder about artintate or tate on this ground field. So I have to say what this is here. So I guess you can guess it. So dTm was the subcategory generated by the constant sheaves up to twists, and this is simply En lower star of z twist k, where k is an integer as before, and n is some number, right? So we take all, basically, not only the constant sheaf on Gm, but rather also all these kind of nth roots of it, if you like. Yeah, and if we do this, we get some other functor, which we can call psi, and it's true that this reproduces that functor. Yeah, so in some sense, we have a choice of how much, what to put here, and then we get different we get different functors. So what is the reason to prefer this psi over the upsilon? The reason is that this psi behaves much better, the full nearby cycles behaves better, because it is, as Ayub shows, a monoidal functor. And that's what we want, right? We want not just a random functor here, but rather we at the very least wanted to preserve tensor products. So here is a fact, which is due to Ayub. So let's say we have two x lives over A1 and y lives over A1 as well. And then what Ayub shows is that psi for this x here of some sheaf, this will be over the special fiber of the x, and then we can tensor it with psi of g of some sheaf living over the y. And that is, he shows, isomorphic to psi of f times g, where we take the product over A1 of f box g. And in particular, if x and y are both equal to A1, psi identity is monoidal. Is a monoidal functor from, in this case, sheaves on GM or whatever its fiber is to the special fiber. Yeah, so this is kind of a good, and this would not be true for the upsilon. It really uses this full thing here. And yeah, I should. Okay, this is sort of the reason why this is necessary to look at. And now I want to, and so far this was somehow again a recap of known things. Now I want to end the talk really properly by coming up with a speculative idea of what to do about this. So of course, in this situation, this is all I mean, it depends, or how should I say it? I mean, it's kind of a local story. Yeah? So as you can see from this theorem of Price, because it lives on this little Henselian ring. So it's a local phenomenon that we are looking at here. And of course, if we ever want to have a hope for this kind of a thing there, this kind of forgetful functor, we need to globalize this. And the question is how. And there is, of course, a first stupid attempt, which is just to basically take all nearby cycles altogether. Yeah, so imagine we are on some curve, and we want to try and answer this question. We could, of course, take all the nearby cycles for all the uniformizers at all points. That's possible, but that would, in some sense, just be a I don't know how to say it. Yeah, just copy together all these local informations, but doesn't necessarily tell us anything about how they interact globally. And that was pointed out to me by Timo, who, yeah. And then I was frustrated until I came up with the following, which I think is interesting, but it's really unfinished. Yeah, so don't expect too much. Attempt to globalize this is the following. So there is a theorem, the Thom-Sebastiani theorem, which in the context of état sheaves goes back to Deleuze's suggestion and then was implemented by Éleusis and Fou. And so let's say Deleuze, Éleusis, Fou in the case of analytic sheaves. And in the context of motivic sheaves, there is a very recent work by Descombes who does the following. So what I'm writing down is not exactly what he does. So there is a little bit of an epsilon here, but I don't want to claim anything here for this epsilon, but rather sort of I'm just trying to say I'm not stating it the exact same way as Descombes does. So what is his statement? So again, we will work over a field of characteristic 0. This is this is not supposed to be a critical assumption, but just one that is related to the fact that the definition of the full psi is more complicated otherwise. So anyway, let's allow ourselves this restriction, and then the statement is the following. Let's pick two functions, and Tom Sebastiani relates the nearby cycles for f and g to the one of f plus g, so which is supposed, or which is a function from x times x to a1. Okay, so we have these functions, and the statement is there is an iso as follows. So we can do this psi mon for f of some sheaf f. Okay, nearby cycles including their monodromy. Yeah, so now monodromy is, sorry, I should have written psi mon there. I apologize. So psi, the mon refers to the fact that we see this monodromy including this kind of mini Galois group action here. So there is an isomorphism of this guy, and then a certain additive convolution psi mon g of g, and this is isomorphic to something related to the nearby cycles of this function f plus g of f box g. Okay, so let me parse this statement. So f and g, I have said psi mon is this full nearby cycles functor, and what is this box mon? Box mon means the following. So maybe since, yeah, okay, I think I can write it down. So before doing this, I mean, this psi of f will live where? It will live on the zero set of f. So let me write it maybe like this. And then it will have this extra GM factor. Okay, so you can think of this really as a sheaf living on the zero set times GM, if you like, but I prefer this way of writing it. So this is where the first factor here lives. And then there is a similar one for the other one. The zero locus of g, and again datm of gm. Okay, so far so good. This is where it lives before doing the psi mon, and now this the box mon, and this box is doing the following. So we push forward from. It doesn't really do anything on this first factor. It only concerns these two factors, and there it is what you think it is. So you are basically on gm times gm. You push forward to a1 times a1, and then you do the addition to land on a1, and you do star push forward along these maps. Yeah, so this star push forward along these maps, and this lands you in where? It lands you in dm of the zeros locus of f times the one of g, and then finally times and then in order to land back on gm, we want to at the end of the day restrict to the gm. Yeah, so this is what the box mon is. So tensor datm gm. Okay. So that's so it's basically the additive convolution in the star push forward sense of these monodromy operators. That's what this box mon does. And what is going on the right hand side here? Here something similar is happening. Here this I additive is just the inclusion of the zero locus of f times the zero locus of g inside the zero locus of f plus g. Yeah, so because before this lives on that locus, and then we have to restrict it to even be able to compare them. This is Descombes' Tom Sebastiani, and I mean stated in this somehow in this form here. And another mini epsilon is also that this is not only true for the addition, but also for the multiplication. Yeah, so we can do times here, and then we do times here, and then we do multiplicative here. And we again get a similar inclusion with a times there. Okay, so in other words, we see these nearby cycles. For if we collect all nearby cycles whatsoever for all functions on x, they are closely related. And so what I'm trying to somehow suggest, but this is really just a dream for the moment, is the following. So we can say, let's say x is some affine scheme, just to sort of simplify it. And then we can say, okay, such an affine scheme is as good or as bad as its ring of functions together with, of course, addition and multiplication. Yeah, so this sees as much as the variety itself. And so we can maybe try and organize all these nearby cycles functors into some sort of a ring structure. Yeah? So maybe let's say question, and then I will stop. Question, can we organize all psi f of f for all f's? So let's say maybe psi f and then psi f plus g, etc. of f box f and so on. Can we organize them into a kind of a ring structure, in whatever sense? Yeah. So into a ring-like object. I don't even yet know what I'm trying to ask here, but sort of the idea, I hope it's clear that these Thom-Sebastiani type theorems might give us a clue on how to organize all these nearby cycles into one well-behaved being. Okay, thank you very much.
Thank you very much. Are there questions?
Yes.
So you gave an example that was kind of trivial. Are you able to do maybe a non-trivial example like A2 to A1, the multiplication map? Or is this already unbelievable?
You mean computing nearby cycles in that case?
Yeah.
Yes. Yes, this can be done. It's still reasonably trivial using sort of, Gaussian type computation. So thanks for asking. So if I claim this here, then what is the argument for doing this? One reduces it using Ayoub's techniques to the case when f and g are the constant sheaf, and this is x is A1 itself. And then you have to compute exactly nearby cycles for the addition map, or in the purpose version for the multiplication map. Yes.
Okay, I see, but it's tractable.
That is doable, and on top of that, yeah, there are more computations, but I was focusing on the absolute Toy example. Yeah.
And then one more question. So in the beginning, you assumed that X was a scheme, but could you have gone through this whole story with X being like a stack?
Yeah, sure. That's for free. One of the properties of all these functors is that they commute with smooth pullback, because in this I upper star j lower star thing here, clearly this will commute, and so therefore you can descend it along any smooth cover of anything. Yeah. Mm-hmm.